Yeah, friend, please go ahead.
Yes, okay. Good evening, everyone. I'm Afrin, speaking on behalf of Dr. Abdul Ghafoor, Senior Consultant in Infectious Diseases and Managing Trustee of AMR Declaration Trust. The AMR Declaration Trust is a public charitable trust founded on the principles of Chennai Declaration Document and Initiative. Our primary mission is to stimulate discussion, inspire action, and explore innovative solutions to address the global challenges of antimicrobial resistance. We sincerely acknowledge the unrestricted educational grants from pharmaceutical companies such as Viatris and Pfizer, which have enabled us to organize these webinar sessions free of charges to attendees. So here we have with us today a diverse panel of experts to speak on the webinar topic, environmental challenges and mitigation measures in hospital. So representing the field of infection diseases, we have Dr. Yamuna Devi, consultant in infectious diseases and control at Apollo Hospitals, Chennai. She's our session coordinator, and Dr. Anup Warrior, lead consultant in infectious diseases, Aster MedCity, Kochi. And we also have joined by experts in hospital infrastructure and facility system, Mrs. J. Jamila, senior lead engineering manager at L&T Constructions, a member of ISHRE and an HVAC specialist, and Mr. K.B. Vinod Kumar, head consultant and managing partner at VBG Consulting Engineer and chairperson of the Engineer Forum in Healthcare CHO. So to begin with the session, now I invite Dr. Yamuna Devi to give a brief overview of today's main topic, environmental challenges and mitigation measures in hospital. Please, madam.
Thank you, Afrin. Good evening, everyone. I would like to thank all the faculties who have joined with us to share their expertise knowledge on these infection control. We all know that the environmental control in infection prevention within the healthcare setting is a very important topic. And also, it's a very critical challenge in the hospital because it directly impacts the patient safety and healthcare worker well-being and overall healthcare quality. The environmental controls serve as a fundamental line of defense by reducing the presence of harmful pathogens in the healthcare environment, which not only includes ventilation purpose, the overall HVAC system, the maintenance of it, and also the accreditation standards, which has to be at par in order to prevent infection for the patient. Beyond protecting the patient and staff, robust environmental controls contribute to lowering the healthcare cost by preventing infections that often require extended treatment and hospital stay. And moreover, adherence to these established guidelines and regulatory standards ensures that the healthcare facilities maintain safe and compliant environment. So today, as we explore the latest strategies and innovations in the control measures, I look forward to a very rich and insightful discussion that would help us to have a better safeguard our healthcare environment and also improve the patient safety.
Okay. Yes, madam. Thank you, madam. So now I invite Dr. Anup or Warrior, lead in consultant in infectious diseases at Esther MedCity Kochi and Group Chief of Medical Affairs and Quality for Esther. He brings over 18 years of experience in clinical infectious diseases, hospital infection control, and antimicrobial stewardship program, along with 11 years of expertise in healthcare quality and medical administration. He will be speaking on environmental challenges in engineering control in a healthcare setting. So kindly please give us a good input on it, sir.
Thank you. So just allow me to share the screen. So are my slides up there and visible?
Yes, sir.
Yeah, okay, thank you. So good evening all. So the title was a bit tough, so I had to read it 2-3 times to actually understand what would be the focus point of this, the environmental challenges of or in the engineering controls in infection prevention in the healthcare setting. I hope the data and the information which I am able to share links closely to what my next speakers are going to speak, specifically about the HVAC. Now, the environment does not mean only the air or the ventilation systems. We have surface to person contamination. So environment, the built environment, as it is called, also forms a part of this concept of prevention or engineering controls to prevent transmission of infections. Then obviously you have the airborne or inhalational, which the majority of the sessions today is going to be about handling air quality. There is also water involved as a risk, as an environmental risk in healthcare. So overall, in the next 15-20 minutes, I will be sharing the challenges from the built environment, challenges from the air quality, indoor air quality, and the challenges from handling the water in the healthcare facility. So starting with built environment and inanimate objects, this was a systematic review just published last year. We know that intensive care units form one of the major place where a lot of hospital-acquired or nosocomial serious infection do occur, primarily because of the patient vulnerability and the invasive interventions that happens in the ICU. So in such a vulnerable, high-risk setting, most of the patient care equipment, especially those which tend to be shared, like sphygmomanometer and stethoscopes, are identified as very common fomites in the ICU. These are also pinpointed as reservoirs of a lot of nosocomial pathogens in the ICU. So this is one example of how inanimate objects in the environment harbors the potential to transmit MDR and drug-resistant infections onto your patients in the ICU. We have recent data also published regarding the Clostridium difficile transmission in the ICU, where again, in this case, rather than the inanimate fomites or patient care equipment, the built environment itself, including the clot, the floors, the sink, etc., have also been identified as reservoirs for Clostridium difficile. So just to reiterate that both patient shared equipment and the built environment contribute to hospital-acquired infections, which requires our interventions in the form of developing into reservoirs. If you look at the persistence of pathogens on these inanimate surfaces, it's interesting to see that the Klebsiella persisted the longest, with a range leading up to 600 days. And we do know that Klebsiella pneumoniae forms one of the major sort of an endemic drug-resistant pathogen in our healthcare setting, which is responsible for a majority of our difficult-to-treat infections in our ICUs and even non-ICU settings in the hospital. So attention to built environment and patient equipment forms a very important part of infection prevention. Now, from the engineering control perspective, it is not just what kind of disinfectant we use to disinfect the environmental surfaces in healthcare facilities. So there are a lot of standards in terms of what kind of disinfectant should be used, etc. But it's more about how these disinfectants are applied, how the cleaning process happens, how the dilution and contact times are provided, etc. So a lot of this, the environmental disinfection and the sanctity of keeping the environment clean or hygienic depends upon not just what kind of disinfectant or material you use, but it's also about the practice of exactly how these disinfectants are applied, how do you dilute them, you maintain the concentration, and how do you give enough contact time, etc., etc. Now, what are the challenges with surface contamination with us? So one is that it's a 24/7 ongoing activity. Right? So both surface contamination and need for surface disinfection is a continuous activity. It is very difficult for us in a healthcare setting to get a non-operational state in the hospital with no patients. So very rarely do we have a chance of completely evacuating a ICU, or unlike the operating room or cath lab, to get your wards or ICUs completely evacuated for a deep cleaning and detailed environmental cleaning and disinfection often is very difficult. Even in the rooms, there is a pressure for turnaround time of disinfection. Right? So especially when there is a blood pressure and more of admissions waiting, the tat of giving the room to the next patient becomes very crucial, and people often tend to shortcut this disinfection time. The patient care equipment, the kind of disinfectants in terms of safety of chemicals and handling by the healthcare worker becomes important, because this may be toxic both for the patient or those who may handle them. And finally, we do not have a system of doing a competency assessment for the performer, the actual staff who does this environmental disinfection. Now, can we have engineering solution to all this? I'm not going into that, just leaving you with this question. One of the things which had come up was the aseptic, the non-touch disinfection techniques like hydrogen peroxide misting, or the chloride-based mixing, etc., where a robotic dispensing of smaller particles of disinfectants into the air settles down into the floor, and it helps as an adjuvant for the mechanical surface cleaning. So there people have been looking at engineering solutions like what we discussed earlier. But this is one area where we really need engineering to get much more into depth, because depending upon the cleaning staff at the site to do the right job, give the enough time, constant, etc., is a bit challenging. Lot of variables there, and here is somewhere the engineering solutions might help. The second part of is about the air quality, indoor air quality. So we had two nice guidelines from the World Health Organization, one in 2009 and another in 2021. And both of them, along with the patient safety, they also focused on the healthcare worker safety. The first was the guidelines for indoor air quality, focusing on dampness and mold buildup in the healthcare facilities. And second was immediately post-COVID, a roadmap to improve and ensure good indoor ventilation. Okay? Because a lot of respiratory infections, flu, RSV, tuberculosis, obviously, we had measles outbreak, chickenpox, a lot of them can be tackled with good indoor ventilation. This was a publication slightly before this COVID guidelines were present. Anyway, we had the National Airborne Infection Control Guidelines even before that. And through a questionnaire, sort of a qualitative research, the healthcare facilities in and around Kerala and even few outside were reviewed for how much of them had implemented the National Airborne Infection Control Guidelines. And in fact, less than 40% had any significant parts or components of this guidelines implemented. That means majority, 60% plus, did not have almost anything related to the airborne infection control in their settings. So though guidelines are there, starting from the WHO to the National Airborne Infection Control, the implementation in our hospitals are grossly lacking, a lot more to do in this aspect. Now, if you look at what are the airborne pathogens we are worried about, so this is from the CDC, and it talks about the pathogens under the reported incidents. So Aspergillus and Mucorales have the highest evidence for airborne transmission in terms of report, along with Mycobacterium tuberculosis, measles, and varicella. Occasional reports have been there with other fungi species. Among the bacteria, Acinetobacter is important for us. Staph aureus is important for us. Virus, obviously, influenza, RSV, this is what we spoke about. The others have not been able or not been published a lot in terms of indoor air transmissions. So definitely you have fungi like Aspergillus, bacteria like Acinetobacter and Staph aureus and Streptococcus, and a lot of other viruses which are important transmissions through the air. Now, what are the challenges with airborne infection prevention and control with this? We always think of airborne with measles, chickenpox, and TB. Okay? But there are more pathogens than we think who can be transmitted airborne or inhalational, as the new term, which includes serious nosocomial bugs like Acinetobacter also. From the design perspective, with the guidelines, we have either an option of going for natural ventilation or an HVAC, humidity ventilation and air conditioning systems. But these have high energy utilizations, both in installation and operational costs. And with this, there is a lot of shortcuts and incomplete implementation of these standards, the HVAC standards, all around the healthcare industry. There is also a huge lack of awareness about the indoor air quality, specifically with the focus on the us healthcare workers. We spend a majority of our time in this environment, the hospital environment, and the poor indoor air quality is shown to have significant impact in terms of both physical and mental health. Lack of awareness of both the employees and the employer or the management regarding the importance of indoor air quality, lack of monitoring indoor air quality. So here again, we seek engineering solutions. which are cost effective. Even though theoretically we are able to link hospital-acquired infections, length of stay, etc., to the cost, when it comes to the practical reality, when it boils down to Excel sheets, unfortunately, these links are not very evident. While installation and maintenance of HVAC, the costs are very evident. So we need either a better way of communicating why we need this, or we need the engineering solutions which will be more cost effective, so that these costs seem reasonable and worthwhile going forward. Finally, the last risk from the environment in our setting is water. This is a snapshot from the CDC water management program. So they recommend that you should have a comprehensive water management program that identifies the hazardous conditions and where you can take corrective actions that can limit the growth and spread of waterborne pathogens in hospitals. For that, you need to do what is called as a water infection control risk assessment. It looks at the water sources, the mode of transmission, what kind of patients are placed there, and how well are you prepared to address this. There is a specific point addressing how do you reduce exposure from sinks and drains. Okay, and I will show you two literature also to support the importance of this design in sinks. And they again focus upon intentional sink design choices that can prevent splashing. So this is the healthcare facility water management program checklist, which is a sort of document which can help you out to select what are the parameters that you right now have, what are the gaps, and what you need to actually to fill in those gaps. Now, coming to why so much of focus on sinks, right? Both in assessment of risk and also in design of sinks. So this was a systematic review, sink interventions in the ICU to reduce risk of infection or colonizations. This comprised of multiple observational studies. These are mostly set up in outbreak settings. But though these were not randomized controlled trials, but in spite of that, understanding the limitation of observational studies and outbreak setting, the interventions which either modified the design of the sink or removed the sink to prevent splashing contributed a lot in terms of reducing the gram-negative infections. This is another publication a little later into the month, another systematic review, impact of sink removal and other water-free interventions, where both outbreaks of GNB, specifically Pseudomonas and non-tuberculous mycobacteria, were evident. This is another checklist or a document for us that if at all we have these waterborne outbreaks, Pseudomonas or NTMs or even other Enterobacteriaceae like Klebsiella, etc., this is an assessment checklist where you can assess the water quality and infrastructure to help you investigate the potential water-associated infections. Okay, so this will help you again to understand in your facility from the engineering aspect what can be done to avoid risk of waterborne transmission. This is the template of water risk assessment. I will not read through that, but just to illustrate that it is divided into 4 components. You assess the water sources, you assess the modes of transmission, you look at the patient susceptibility, like in BMTs or in general patient weights, and finally the duration of exposure, high, moderate, low, etc. And then categorize, give a score, and then try to prioritize your resources in addressing that risk which has got the highest scores. A big list of opportunity pathogens that can colonize and have been proven to spread through waterborne. Okay. Gram-negative, a lot of them. Pseudomonas, Burkholderia, Acinetobacter, all of them very familiar. Whenever you see bugs like Ralstonia, Spingomonas, Elizabeth Kingia, etc., be very, very wary of this risk, of this waterborne outbreak risk. Others we have already spoken. Mycobacteria like non-tuberculous mycobacteria, a big list of non-tuberculous mycobacteria can spread through this. Common yeast, including Candida, can be there. Aspergillus, including in BMT units from the showers, it can also have a waterborne spread of Aspergillus, and few protozoa, especially Acanthamoeba and Naegleria. From the engineering perspective, we have significant difficulties in addressing waterborne risk, specifically because the piping material may not tolerate the kind of disinfectant and superheated steam which might be required. The design might have stagnations which will prevent the disinfection from acting, or support growth of biofilms which will make it difficult for us to actually achieve disinfection. So this is one area where starting from the design phase itself, it's very, very important, very difficult to go back and rework the plumbing, etc., to correct these deficits once it has happened, right? So this is a guideline for overcoming the biofilms, which focuses upon the aspect from the design, what kind of products you use, and then finally ends up with the effective disinfection protocol. So here the engineering involvement is very, very critical, starting from the design stage. So what are the challenges with waterborne infections for us? We have gram-negative outbreaks from the water exposure in the ICUs, the sink placement, the way they are placed, either nearer to the patient care or where the medications are prepared, the design that should prevent splash, difficulties with plumbing disinfection and the impact of biofilms, limited opportunity of non-operational status, especially when we are using high concentration chemicals or superheated water. It may become safety issues to the patient and the healthcare workers if they use it in between. Very poor awareness on the water risk assessment, rarely done or practiced in our part of the world, and very inadequate monitoring of water quality protocols. Again, so hence, this is one area where a lot of interventions and inputs from the engineerings are sought. So to close my discussion for today, to enumerate some of the challenges from the environment regarding the engineering controls are: one, to start with, there is significant lack of awareness about engineering standards for surface, air, and water management in healthcare settings. This is coupled with no regulatory oversight, with a significant cost impact of many interventions. So lack of awareness, no regulatory oversight, and high cost, all of them means poor implementation of the standards for engineering controls in a healthcare setting. There is adverse impact on patients, especially those who are vulnerable in ICUs or immunocompromised, etc. And importantly, also the healthcare workers, because we spend a majority of our day in the hospital breathing this air. We need to promote cost-effective and safe engineering solutions, along with some sort of a regulatory oversight and monitoring, so that the healthcare engineering standards pick up and we are able to keep to those standards which ensure our patient safety. So that's all from my side. You're on mute, Afrin.
Unmute, Afrin. Still, we can't hear you. So, thank you, Anup sir. That was indeed a wonderful lecture. The theme was engineering control, but we were restricting it for HVAC. But you covered completely the challenges which is faced as healthcare providers and the administration and the infection prevention and team related to the water control measures, which is on and off. We keep getting some or the other growth in the water, and the challenges related with water area disinfection is all the more difficult because the drains, which comes with a U-can shaped drainage where there may be stagnation of water, cleaning with disinfectant is not possible. We can't reach out to those areas with brushes. So that's the major challenge where we are left out as part of water control goes. We often see a lot of outbreaks being mentioned in Western guidelines related to Legionella, but related to water control measures, as far as our country goes, we have not seen so many Legionella diseases or Legionnaires diseases related to Legionella pneumophila. But of course, we do see a lot of multi-drug resistant organisms linked directly with the sink used within the patient care areas, which has caused a lot of outbreaks in the system. When we keep monitoring these places, when we do a lot of environmental swabs or collection of sample, we don't find it. But ultimately, when we go and swab from the sink, from the faucet areas, or the place where it drains, we could find out a lot of carbapenem-resistant Klebsiella and E. coli, and that's where all the contamination ends up and keeps aerosolizing when someone goes and washes their hands in the hand wash sink area. Thank you very much, sir. So, Afrin, are you able to connect, or still you are having problem with your network?
We can't hear her. Afrin, can you try from another instrument like a phone or a laptop? Change them. Dr. Anup, good evening.
Good evening, Vinod. Good to
How are
meet you.
you? Yeah, pleasure to meet you. I like the best was the water risk assessment. I think nobody has ever thought about it. It's one good topic that I think we should think about doing.
Correct.
Because we do a lot of risk assessments as part of JCI and AACI, but there's never something specifically done for water risk assessment. Is there something that can guide us how to do it, the format, or?
Yeah, as I was showcasing the CDC template,
Yeah.
it's a very straightforward checklist.
Okay.
Like
Would
a
you
Excel
be
no format.
shared by the team here in PDF?
Yeah, if you want, I will share it with you on WhatsApp.
No issue, because somebody was asking for it. I had sent this
Sure.
link to many people, and many people said it's
Sure.
wonderful.
Sure.
Dr.
So,
Yamuna, is it possible
yeah.
to get the PPTs and in PDF and share it among the team?
Sure. I will.
Some of the participants have written to me in just a few minutes ago asking for that.
Sure. Definitely, we'll do that. So, since Afrin is taking her own time and because of a network issue, I would like to call upon Mrs. J. Jamila to go ahead with the next topic on HVAC mandatory requirements in high-risk areas pertaining to operation theatre, cath lab, ICU, and transplant unit.
Thank you, ma'am. Yeah, I'll just start my presentation. Is my screen visible?
Yeah, Jamila, your screen is visible.
Okay. Fine. So good evening all. So today our topic is like the mandatory HVAC requirements in high risk areas such as OT, cath lab, ICU, and transplant units. So we'll cover it up today. The contents are like the codes and references we need to follow, and then the general arrangement of an OT AHU, and the ducting, air distribution, and the ducting and the material, and the laminar airflow pattern, and high sensible radiology rooms such as cath lab and ICU and transplant units, and strategies for mitigating environmental challenges, future trends and innovation, and the case summary. So the contents will be like this. So codes and references will be like for the HVAC design, we used to refer like NABH, ISO, and as well as the ASHRAE 170. The common ones is like NABH and ASHRAE 170. Moving on, it's like OT, as you all know, like operation theater is an aseptic environment where the operations are carried out. So the bacteria carrying particle should be swept away from the patient table. So there are two types of OTs, like super specialty OTs and general OTs, that is type A, type B OTs. So NABH class 2018, it covers the major parameters, the design temperature, what we need to maintain. That is, it should be like type A OT, that is a super specialty OT, and type B OTs. It is almost all the parameters are same, except a few. So the design temperature shall be like 21 plus or minus 3 degrees Celsius has to be maintained. And relative humidity shall be like 20 to 60%, but an ideal condition should be like 55% RS should be maintained. And fresh air, coming to fresh air. So fresh air, that is the minimum outdoor air ACPH shall be like 20%, that is 4 ACPH. And the total ACPH shall be like 20 ACPH. And the pressure with respect to the adjacent spaces shall be like minimum 2.5 pascals. And but the CDC that calls for like the room air pressure should be like 8 Pascal. And air velocity at the patient table, that should be like 25 to 35 FPM. That is at the patient table. So at the grill, it should be like 90 to 120 FPM, so that the air which shall be like it will be like sweeping away the bacteria carrying particles away from the patient table. And again, the air quality, it is like supplied through terminal HEPA filters. And the other 2 stages of filtration shall be inside the AHU, that is the air handling units, pre-filter and fine filter, it will be there. Third stage, that will be HEPA filter shall be at the terminal HEPA plenum inside the OT. And air filtration, that should be like, it should be like a class 100 ISO class 5 at rest condition should be maintained for a type A OT. And a class 1000 ISO class 6 at rest condition should be maintained for a type B OT. And also at all times on operation theater, that should be like positively pressurized, and during operational and as well as the non-operational hours. So that is one criteria which needs to be taken care, so that there won't be any growth of microbial conditions. And again, when it is coming to 100% pressure system, see, for type A and type B OTs, generally we go with like recirculated air, that is 20% only we will be giving fresh air, and balance 80% shall be like recirculated as per the boards. But when it is coming to septic OTs, where the burn treatments are happening, it should be like 100% fresh air should be given. So for such kind of air handling units, we'll be having like energy saving devices like a heat recovery wheel or the runaround pipes. Such energy saving devices shall be used actually. And one more thing is, in the inside condition, see, type A and type B are almost like 21 plus or minus 3 degrees Celsius for both, but except one OT, that is the joint replacement OT, it should be maintained with 18 plus or minus 2 degrees Celsius. So that is the one thing. For maintaining 18 plus or minus 2 degrees Celsius, we should have a separate system, that is a DX coil system, apart from a chilled water coil system. Coming to the ISO clean room standards, it is like, see, the 0.5 microns and the larger particles, that should be like for an ISO 5, that is for the super specialty OT, the acceptable particle count is 3,250 numbers. And for ISO 6, it is like 35,200, 0.5 microns or larger particles. So this is the ISO clean room standard states. And coming to the air changes, it is like as per ISO clean room standards, it is asking for 300 to 480 ACPH for class 100, and for class 1000, it is like 180. That is the filter coverage. The HEPA filtration coverage should be like 60 to 70%, it is mentioned. And for class 1000, it is mentioned like 20 to 30% of the filter coverage of the room area shall be maintained with the filter coverage. And the CFM per square feet shall be like 36 to 65 CFM per square feet and 18 to 32 CFM per square feet. Here, there is one practical challenge we have. Say, for example, OT, it is like 65 square meter or roughly around 700 square feet. Okay, so NABH was calling for like 20 ACPH, the total ACPH. If we go with that, it will be like an air handling unit for a OT shall be like, the capacity shall be like 2,500 CFM to 3,500 CFM roughly. Okay, but if we are going with this standards, it is practically impossible. It is like a 300 to 480 means it is 40,000 CFM for one OT. Space constraint and so many issues are there. So generally we go with NABH standards. Just I'm bringing it to your knowledge on this part. Otherwise, it is like it is mentioning like filter efficiency, that is HEPA, and that is 99.997% efficiency should be there. And sealing type, it is mentioned aluminum T-bar grade, and light fixture type, and ceiling panel, wall system, flooring cover, flooring base, everything should be taken care. And air return shall be like, it will be at the lower side. So return air shall be collected at all 4 corners of the OT. And it will be like, the returner bill shall be like 300 mm, that is 1 feet from FFL. It will finish to floor level. It will be like that actually. so that the laminar airflow pattern shall be maintained. And moving on to ASHRAE 170, ASHRAE 170 talks about ventilation of healthcare facilities particularly, and we follow it majorly. So ASHRAE 170 talks about regarding filtration efficiencies, it is like it is asking for 2 filter banks. That is, even for the operating rooms, ASHRAE 170 calls for like MERV 7 and MERV 14. MERV 7 is nothing but pre-filter, and MERV 14 is nothing but the fine filter to filter the fine particles. Okay, but even though ASHRAE 170 calls for like 2-stage filtration, we generally go with the HEPA filtration also inside the OT to maintain the laminar flow and as well as the Tier 2 clean room standards. And for ICU, it is calling 2-stage filtration only. So MERV 7 and MERV 14. And coming to the supplier outlets, so operating rooms shall be having like it should be like the non-aspirating type of airflow. That is nothing but the unidirectional airflow, that is the laminar airflow pattern, so that the turbulence shall be avoided to the max possible. And ASHRAE 170 also, it is similar to NABH standards only. So operating rooms, we have to maintain like a positive pressure at all times during operational and as well as the non-operational hours. And outdoor ACPH, it is 4, that is 20%. And total ACPH shall be 20. And coming to the RH, it is like 20 to 60, it is asking for. And design temperature shall be like 20 to 24 degrees Celsius. So this is how an ODHU shall be looking like. See, this is nothing but a double-deck AHU, which is roughly around, say, for example, for the 2500 CFM to 3500 CFM itself, it will be measuring to nearly like a bus, it will be like 4 meter. So 4 meter, it will be approximately length, and width shall be like 2 meters, and the height shall be like 1.88 meter. It is close to 2 meters. So this is how an OTH shall look like. So this is nothing but the returner damper, and this is the mixing chamber. This is the pre-filter, which is nothing but the MERV7 filter. And this is the cooling coil, and this is the heating coil, and this is the UVGA lamp. And this is phase and bypass damper to adjust the relative humidity. And this is the drift eliminator, and this is the blower. And this is the back filter, that is the fine filter, which is nothing but the MERV 14 filter. And this is a supplier damper. And also this is an optional element, but in some cases we have. So this is nothing but the returner fan, which is also having a returner damper and a pre-filter and a blower, and as well as the exhaust air. Also we have a returner damper here to mix. This is the mixing chamber. So part of it can be mixed and part of it can be exhausted out as well. Each shall be looking like. So each OT, say for example, in a hospital, if we have like 16 OTs plus 2 emergency OTs, like that, whatever we have, whatever the number we have, we'll be having like each OT shall be having a dedicated AHU that shall be placed in either in the service floor or in the terrace floor or in the same floor, which will be having an AHU room to locate. So this is how it will be like. And coming to the air distribution pattern, it is nothing but, see, this is the supplier duct. The blue color is the supplier duct. So it is coming from somewhere like a service floor or terrace floor or whatever. And it is coming, and this is the HEPA plenum, which will be having the SS perforation inside the OT. That will be the thing we will be saving from the OT. And this is the terminal HEPA plenum, which will be having 4 connections so that the supplier duct will be connected here. This is the patient table. So it has to cover the entire patient table so that the airflow shall be like unidirectional, and it will be sweeping away the bacteria carrying particles. So the supply will be always from here, and the return shall be collected in the corners of the OT, 4 corners. So returner grill shall be like, it will be looking like this actually. So returner will be collected at the bottom in the 4 corners. So this is how it will look like. so that uniform airflow shall be maintained. And coming to the duct material, actually there is no code which is explicitly talking about the ducting material which needs to be maintained, which needs to be followed in an OT. It is only ISO 14644. It just talks about that there should be a smooth, cleanable, and non-contaminating surfaces which should be maintained so that the bacterial colonies or anything can be avoided. It will be also corrosion resistance, and it can be cleaned and sterilized easily. So such kind of material can be used in one such material is nothing but the aluminum. That's why we, as an industry practice, in an OT, we generally go with aluminum ducting. And also we have a thermal insulation which needs to be followed. So aluminum ducting, generally we are going with nitrile rubber or any other nitrile rubber. Mostly we go, it will be like 25 mm thick for supply duct and 19 mm thick for return duct. And generally for OT, we don't go with acoustic insulation because inside the duct, if we are going with acoustic insulation, it will lead to create some more dust. So generally we don't go with acoustic insulation for OT supplier ducts. So we generally have the AHU which will be located in some other far place. So in that distance itself, it will be the noise shall be curtailed. And this is how the laminar airflow pattern inside an OT shall look like. So just I have mentioned here. So this is how it will be like. Okay, so that's all about OT. With the limited time, I could cover all the things about OT to some extent. There are much more to talk. And coming to high sensible radiology rooms, see high sensitive radiology rooms are nothing, not only cath lab, there are other radiology rooms also. Just I'm touching on it. Linac bunkers are there, and then CT scan rooms are there. Sorry, CT scan rooms are there, and MRI, PET CT, SPECT CT, gamma camera, CT simulator rooms, HCR brachytherapy rooms, cath labs, and DSA rooms. So since the topic mainly talks about cath lab, I would like to cover about cath lab. So cath lab will be having like 3 areas: the cath lab, equipment room, and console. So the temperature which needs to be maintained is 20 to 24 degrees Celsius in all the 3 areas. And RS shall be like 30 to 60. The ideal condition would be always 50 to 55. And inside cath lab, the heat dissipation shall be like in cath lab 10 kilowatt. And in an equipment room, it shall be like 5 kilowatt. And in a console, it will be like 2 kilowatt. So cath lab, see actually the equipment room will be having much more heat dissipation. That's why always the medical equipment vendor will be having his own external chiller, his own chiller for cooling that heat dissipation of that equipment. And apart from that, whatever the room cooling is required, that will be provided from the HVAC part. So the medical equipment vendor will be having his own chiller. That's what the point I wanted to say from this particular slide. And just I would like to elaborate on the air distribution scheme of LINAC and HDR. Also, it is mostly it is similar for cath lab as well. But only thing is the cath lab will not have this maze arrangement. Maze arrangement will be only for the LINAC and the HDR brachytherapy kind of thing, because to avoid the radioactive materials to get escaped out of this area. So that is why this maze arrangement is there. So generally it will be like, instead of this without a maze arrangement, the cath lab will be looking like, so we can just relate to cath lab as well. So it will be having a supply duct and return duct. So supply duct coming like this, and the supplier grills are there, and then returner grill is on the other side, and returner will be collected, and it will be again going to the AHU. So there is 3 LINAC bunkers in this particular cancer care hospital, LINAC 1, LINAC 2, LINAC 3, and also a HTR brachytherapy is also there. So this is how an arrangement will be. So moving on to the ICU and transplant units, ASHRAE 170 calls for for critical and intensive care, it should be maintained their pressure relationship with respect to the adjacent spaces. Actually, it is not required, but mostly it is positively pressurized. So the outdoor ACPH shall be like a 2 ACPH we need to maintain. The total ACPH shall be like 6. And coming to the relative humidity, it is again 30 to 60, and the temperature shall be like 21 to 24. And each ICU we generally used to go with dedicated AHU. So it will be like there are many ICUs like HTU, and then that SICU, PICU, that surgical ICU, pediatric ICU. So many ICUs are there. No, all the ICUs will be having a dedicated AHU on its own. And intensive care for the burn units, that will be again having like septic arrangement. That's why we will go with the TFA. So actually, ASHRAE doesn't call for like all room to be exhausted directly to outdoors, but generally we go with 100% TFA for a burn units alone, as in practice actually. And again, the RS shall be like 40 to 60 for a burn unit, and maintain temperature to be maintained is 21 to 24. And also when it is coming to intensive care units, generally it will be having a protective environment room or otherwise an isolation room. So AI room is nothing but an isolation room. It will be having like each ICU will be having one isolation room kind of, right? So we generally we go with all the complete air which will be given to the isolation room will be completely exhausted to the outdoors. So the fan will be located on the terrace, and the fan will be having a HEPA filter as well, so that all the infectious element will be filtered, and then only it will be exhausted to the atmosphere. And when it is coming to the supply, from the AHU, there will be an arrangement called fan filter unit, which will be having a HEPA filter, and it will be having its own blower. So the supplier will be connected to the fan filter unit instead of a diffuser, and that will be giving a supply to the isolation room. If it is an isolation room of infectious patient, then it will be like negative pressure shall be maintained. If it is an protective environment room, then it will be like positive. So there it will be like positively pressurized. That is the two difference between that is the difference between the negative pressure area isolation room and the positive pressure protective environment room. So coming on to the strategies for mitigating environmental challenges, nothing but see advanced HVAC designs have been used. Real-time monitoring sensors have been used nowadays, and for the optimum airflow and as well as the filtration, so that real-time data have been collected, and based on that, the airflow and filtrations have been maintained. And again, HEPA filters have been used for certain very critical areas such as the OT and as well as the isolation room. And wherever anywhere else required, also we are providing with HEPA filter. And UVJ systems are always provided in the cooling coil. And zoning and pressure differentials are being maintained for the infectious areas with respect to the clean zones. And smart building technologies, nowadays the IoT sensors integration, that so those elements are also been adapted for real-time data monitoring. And automated energy management for all HVAC and as well as the efficient lighting also been followed nowadays. Smart AHU and smart, all the things have been smart converted to smart. And again, predictive maintenance using AI analytics to reduce equipment failures also been done in several things. And as well as coming to sustainable construction materials, that is nothing but the use of non-toxic, low-emission building materials, and recycled and sustainably sourced materials have been incorporated. And coming to energy efficiency, nowadays we are using like all energy efficient motors, and all the energy efficient precautions have been used as per codes. And natural ventilation also we have been using in wherever possible. And regular maintenance and monitoring has to be done in HVAC, plumbing, and waste management system. That should be scheduled. Inspection should be there as well. And routine testing of air and water quality should be there. And compliance of audits to meet regulatory standards. And again, adherence to OSHA, CDC, and WHO guidelines for infection control. So these are the standards which needs to be adapted and complied for the safety of the healthcare facilities, and documentation also to be done. Moving on to the future trends, like again the same, it is like smart hospitals and IoT integration, and then AI-driven environmental monitoring, and net zero building sustainable healthcare infrastructure. And again, modular construction. Nowadays, modular OTs are more used actually. So modular construction, net zero things are nowadays sustainability. For sustainability, we have been following. And I think I've come to the end of the presentation. I think most of the points I have covered. Thank you so much. So the key summary is like, so today we have seen, like, I think you would have got some takeaways from this particular presentation. So codes and references, and then temperature, what needs to be maintained in high risk areas, and air pressure, air changes, what needs to be followed, three-stage filtration, GA drawing of an OTH, how it looked like, duct material, air distribution, and then laminar flow pattern, and then high sensitive radiology room, what is the temperature needs to be maintained, and ICU also, we just touched upon it. And lastly, we also saw about the strategies for mitigating it and the trends and innovation. So that's all to say. Thank you so much. Thanks for the opportunity. Hope you have got some takeaways.
Thank you, ma'am. Thank you, Ms. Jamila, madam.
Thank you.
Ma'am is a senior lead engineering manager at L&T Constructions with over 21 years of experience in the HVAC field. She has also worked across IT parks, hospitals, and data centers, and has specialized in hospital air conditioning designs. Her notable projects includes Apollo Proton Therapy Cancer Center, AIMS Gorakhpur, and AIMS Guntur, Jipmar Hospital, West Bengal Medical College and Hospital, Patna Medical College and Hospital, and AIMS Rewari. She has been a member of ISHRE since 2008 and previously held associate membership with ISHRE and IEEE. She has also a leadership position in Toastmaster International, L&T, ECC Toastmaster Club between 2014 and 2017. Her recent national level recognition as a HVAC specialist highlights her exceptional expertise. Ma'am, thank you, ma'am. Thank you for your valuable insights.
Thank you
So
so much.
we had a question also. Anyway, sir, Vinod sir has answered it. Yes. So participants are also encouraged to ask a lot of questions during the session. So I now invite Dr. Mr. Vinod Kumar, Physical Environmental Surveyor at AACI and Chairperson of Healthcare Engineers Forum in CAHO. He is an active member of national and international organizations such as CAHO, ISHRE, FSAI, IPC, ASHRAE, and FOCUS. As a hospital engineering consultant, he has designed HVAC system for several premier hospitals in Kerala, including Rajagiri Hospital, Kraft Hospital, Kinder Hospital, Kim's Hospital, Adlex Hospital, TM Hospital, and NS Hospital, as well as hospitals outside Kerala, including Shankara Eye Hospital, Orissa, Holy Family Hospital, Delhi, and Yashoda Hospital, Delhi. Sir will be speaking on accreditation prerequisites for HVAC system and preventive maintenance protocol in OTs. Vinod, sir?
Yeah. Thank you, friend. Can I start sharing?
Yes, sir. Sure, sir.
Visible?
Yeah, it's visible, sir.
So good evening, one and all. Thanks to AMR Trust to having invited me for this webinar to speak on accreditation requirements for HVAC facilities and what are the maintenance requirements that are basically done specifically to the air handling systems feeding to the operation theaters and critical areas. My name is Vinod, and as Efren has mentioned, I'm a hospital consultant. And let's move into the today's program. Now, I'll be talking about how the accreditation standards are well connected to the engineering facility infrastructure and specific to the air conditioning systems. So we'll be talking about three standards. One is the NABH 6th edition, American Accreditation Commission International, and Joint Commission International standards, which relate to the systems and processes that you need to follow that will actually make your infrastructure facility in line with the requirements to handle the indoor air quality and the infection control measures that are needed in all critical areas, including your theaters, ICUs, BMT areas, etc. Now, starting with the 6th edition, let's talk about how the standards talk in terms of facility management. Now, FMS 2A, as part of the FMS chapter, says the facilities and space provisions shall be appropriate to the scope of services. Few minutes ago, Jamila was talking about various kinds of rooms, LINAC, CT scan, PET, SPECT, gamma ray, MRI, all of them have their own kinds of, technicalities in terms of biomedical requirements. At the same time, when it comes to the other utilities, there are requirements which are specific to those, like the air conditioning systems, the kind of materials used for false sealing, the flooring, the cabling, the power supply, the UPS power supply, the backup power, all the requirements like medical gas, oxygen, and suction lines. The lighting, the safety features, the fire and safety requirements. There are various aspects to the facility provisions required for each and every requirement that is connected with the clinical services that the hospital is going to provide. So what is mandatory as per the standard is you need to follow the basic guidelines that says how the facility has to be designed, first of all, how the facility has to be planned, like ARB guidelines, like just now Jamila once again talked about ASHRAE standards, the fire and safety standards. These are various standards which are specific to those particular products that provide the clinical services as intended by the hospital. Similarly, manufacturers' recommendations have to be considered in terms of the design aspect of the building, which includes the structural and architectural demands and design, as well as the MEP design. So we have to be very clear with the facility design and the space provisions required for any kind of facility requirements which are connected to the clinical aspects of the building. Now, what is here 4A talks about is that you need to have a long-term planning for any kind of systems that you do. As you know, a hospital is always very dynamic. After the first day after the commissioning itself, we think about modifications. I think all hospitals keep going through a process of modifications and changes over a long period of time. Now, what happens is the facility part of it, the utilities part of it is generally not very seriously thought about it. Like, if you're going to have a system with 5 floors, and then you say that I have more IP patients coming, I need to add one more floor. The floor gets added, but what happens is you are not really looking at how the facilities can actually handle the requirement that is coming to the whole building as an additional floor. Like medical gas has to be included, increased the power supply, the UPS backup power supply, the air conditioning requirements, the water requirements. So what the standard links with the building engineering is that you need to make sure that adequate future provisioning is provided during the planning stage itself so that you can implement the plan as and when it's required during the process of the expansion. At the same time, you can have a systematic method, like you can rent some portions for some time because you will not really need the full power like DG or chiller or any kind of requirements. You can actually select your process in a strategic manner that you will deliver the requirements of the utilities to the end users who are your clients, who are the doctors and the patients. So you should be basically a very systematic and a collaborative approach of the various team members in the system. Like the end user has to be part of the discussions, the management team, the finance, and the engineering team, so that your whole process of planning, including the current requirements and all future requirements, are put together, and then the implementation is put into place, so that once you commission and once you go for staged commissioning and staged opening of the building, it actually helps you without disturbing the existing systems, without actually having to go for a shutdown process. I think it's very clear. We need to have a systematic and a strategic plan. 4B talks about a proper asset management. It's very important. Why? Because as Jamila did mention about, is real-time, real-time auditing, real-time monitoring is very important to find out how good the equipments are performing to deliver the requirements of the end users. Now, if you have to do that, you need to start from the beginning. You're designing it very well. So when I'm designing a particular OT complex, and like Jamila mentioned, 20 operational theaters in a row, OT 1, 2, 3 up to 20. Now the air handling unit should have a reference number, a unique identification number. AHU slash, if the OTs are on the first floor, say FF for the first floor /01. Now what happens is that becomes a unique identification. Now, if you have different branches, different hospitals, then if, for example, the hospital's name is Yashoda, you can say YH, and if Yashoda has got different branches in the location, well, like let's say Sanjay Nagar, like Nehru Nagar. So Sanjay Nagar can be SN, Nehru Nagar can be NN. Now, you create this unique identification process to label every system in the process, in the building, have a proper documentation. Now, when did you buy the equipment? When was the HO purchased? What is the warranty? What is the preventive maintenance program? When was the motor replaced? When is the issue to be condemned? So you can actually have a proper tracing of the product from the day it was manufactured and the time it gets into its end of life in the hospital. So basically, you have a systematic and a documented process of having a unique identification, a document that will log all the data that goes through the day-to-day actions that you really handle with the air conditioning system, so that anytime you open the tracking document, you will know what has happened. Suppose if there's a failure, you will actually know how things would have gone wrong by identifying the real-time data that you actually collected. But one thing is, the process of having a real-time data, monitoring and auditing them, and taking necessary action is basically a kind of a predictive method of identifying a problem that is impending to happen in future. So it's neither preventive maintenance, it's neither nor a breakdown maintenance. It's actually a predictive maintenance. So this whole process gets into your asset management system. So this is what I was trying to maintain, that you need to have a proper systematic method of having an operation and a maintenance plan, which actually enables to have a real-time knowledge of how the equipment is performing during the 24 hours of its operation per day and throughout the year until its lifespan. So what is important is you have to have a good team to actually manage it, a proper operator, a team. For example, in the operation theater, the operator is sitting very far away. The air handling unit is sitting in another location. The HVAC system engineers are different. The nurses are inside the theater. The doctors are inside the theater. How do we really monitor that? You should have a control panel which tells what air conditioning temperatures, what is the filtration clogging levels, what speed the fan is working, what is the temperature of the supply air. There are various aspects which can bring into as real-time monitoring, real-time auditing, and at the same time telling the operator sitting in the remote VMS room or a control panel room to really see what's actually happening with air handlers and the indoor air quality levels as the surgery goes through in each of the theaters. So we need to make sure that every system goes through an operational maintenance plan to make sure that you have a proper day-to-day operating plan, proper method of preventive maintenance, and a shutdown maintenance as well. These are basically talking about the documented operational and maintenance system that you need to implement to have good and reliable systems, so that finally you don't have a problem where the AHU has failed and you had to wheel out a patient from one of the operation theaters to another operation theater. There are issues where nowadays if you can recollect, most of the hospitals are running full. The theaters are running full. So you cannot have a system where you have two HUs for one theater because you have a standard provision. That's literally not a correct approach. So you need to have good systems, good, well-designed, implemented systems, and well-operated and well-maintained systems. So we need to have periodic inspection, periodic calibration of all requirements like pressure gauges, temperature gauges, so that you know that you can rely upon the data that the pressure gauges, temperature gauges, hygrometers are going to give you, based upon which you know what kind of indoor parameters that you're going to give, and what kind of safe environment is available in the operation theaters or the ICUs of the critical areas. Another important aspect what the standards talk about is that real-time facility inspection rounds, which is generally to be planned once every month. Whenever the team goes, it's a multidisciplinary team that goes for the facility rounds. It includes the engineering, the infection control, the nursing, the operational team, the safety, fire safety, the radiation safety people, then the security management. So basically, it's a multidisciplinary team who goes into the various clinical areas for the facility inspection rounds to identify, as per the checklist, what are the observations that they find that are really not in line with the basic intended requirements of each of the systems that are in place in the facility. Now, when you do a facility round, you need to make the observations, find out what are the root cause of the problem that you have seen, put in corrective and preventive actions to make sure that the systems are put back into conditions and the observations are closed within the specific time that you really allocate for each observation. Another important aspect which all these standards talk about is the risk assessment that you need to do before the construction activity or before any expansion activity that happens. Now, whenever you go for expansion, your air conditioning system gets affected, your electrical system gets affected, all the services gets affected. But what we do is, in the middle of the the modification and expansion, you have people walking through, patients are being treated in the middle of it. You have problems that the electricity has failed, there's a blackout, the air conditioning system has dust, there is smoke and smoke and dust coming through vibration, coming through welding of pipelines. There are various aspects that happen when you actually go for an expansion or modification. The standard FMS 1E says that you need to really have a risk analysis done for all the services that are running around the area where the expansion or modification is going to happen. This actually helps you to make sure that the other patient care areas are literally not affected. I'll just give an example. Again, coming back to HVAC system. Generally, we have central air conditioning system in most of the places. If that is running through a particular area where modification is happening, the air handling unit has an option of taking the return from the entire space to the false ceiling and takes it back to the air handler for reprocessing and reconditioning. Now, what happens is, if the return air is passing through an area where expansion is happening, it will pick up the dust, everything coming from the expansion area, and it will clog the filters, and finally the HU will get choked in the process that the supply air gets reduced. As the supply air gets reduced because of choking of the filters, the temperatures in the adjoining patient care areas will start rising. Now, are we having a problem? Yes. Why did we have a problem? We did not seal off the area where the return air was actually getting access into the area where you're actually having your modification and expansion. So this standard is very clearly talking about a risk assessment that is to be detailed for all the services that are going to be providing utilities to the neighboring areas near the renovation space. Another important aspect is what all engineers have to look at is, have all the utility drawings up to date. They should be really as built on the site. When what happens basically is, what is prepared by the design consultant and what is made by the contractor and what is finally installed, all the three of them generally look different. And finally, what happens when you really want to go up and see what's really there inside the ceiling or inside the wall or inside the shaft, you find them not matching with the real drawings. What happens with that is, your upgradation or modifications really get affected because you do not have the real-time drawing. So basically, Standards talk about updating all your requirements, all the drawings to be as per the correct as-built status. Another important aspect of NABH 6th edition is talking about the electrical safety audits. Any electrical system definitely has is a high risk system. So obviously, if you have if you have any kind of faults in the system, that will affect the power supply, that could affect the air conditioners, it could affect your medical gas system, could affect the lift. Any of the utilities can get affected. And final worst of all is if there are short circuits, then it could affect and make a big problem with creating fires. The last so many years, if you take a list of all the fires that have happened in the hospitals, most of them have been related to short circuiting, overloading of the electrical circuits, improper terminations, improper design of cable sizes and panel. The capacity of the panels are designed originally, but then you have taken a lot of additional requirements without checking the status of the existing switches, whether they can adhere to the additions that is required. So obviously electrical risk is a very important aspect of the hospital, because electricity problems, short circuiting, fires, all that is going to cripple the day-to-day operations, and it could also be a life safety issue to the people inside the hospital. So this is mandatory for us as far as the standard is concerned. And we have to make sure that we have the right people to design, right people to operate and maintain the system. That is, if you have the wrong people, an electrician handling an air conditioner, a plumber handling the maintenance of air conditioning system, this we normally see. And what could happen is that it's like asking a person who has a joint pain to go and meet a dermatologist. We can identify how much difference both the disciplines are going to be. This is the same case. This is the case with most of the places where you don't have sufficient people to handle the day-to-day operations and maintenance. So that actually affects the quality of the systems that you put in place. Your operation goes out of control. There are faults going to happen in the products. Issues are going to have issues, tripping problems, and obviously it will affect your patient safety. Maintenance staff generally should be available 24/7. Another aspect is how to really have real-time data of the downtimes of every system. Downtime and the uptime is important to actually identify what's really going wrong with the equipment. When was the problem emanated? Who received the complaint? To whom was it allotted and who completed it? And basically you get to know what is the rectification time. If the rectification time is bit below the benchmark as per the standards, then you're literally having a very good maintenance team, so that your building is up and running all the time and do not have closures because of maintenance issues. Okay, so basically you can have your own team to handle this. You can have AMCs or comprehensive maintenance contract with the vendors or contractors who take care of the regular maintenance and breakdown maintenance, to make sure that your timeline to put the system back, which is called the uptime, is limited and within the limits which is internationally acceptable, and also does not largely affect the patient care throughout the hospitals. And one more thing that I did mention about the asset management system is, when are you going to condemn your system? When are you going to condemn your HU? When are you going to condemn your condensing unit? When are we supposed to replace the filters? If you have a UV lamp inside the issue, when are we going to replace it? You need to have a basic data for all that, so that the end result of having the data of the end of life of every product inside an HU or the HU or the condenser or filters, that actually enables you to track the life cycle of the product and have enough time for you to either upgrade them or replace them or update them as the requirements called for, so that your quality delivery of engineering utilities to the end users is always happening 24/7. Now, wrong product design. Just look at the HU design. Now, Jamila talked about air handling units, and it's an important aspect of a hospital because it is the final air conditioning system that delivers clean, controlled, and conditioned air into the system. Now, every air handling unit has got walls around it. We talk about inner panel, outer panel, and then in between that you have a sandwiched insulation. Now, the air handling unit actually handles very cold temperature. Now, you are going to cool the air and put it into the theater, for example. Now, your intention is to get 18 to 16 degrees for a joint replacement. Now, your air handler supplies 4000 CFM, say 8 tons of air conditioning is working. Now, the reality is that when the air handling unit is working, it takes the chilled water from the chiller or from the condenser, and it basically cools the air and delivers it into the operation theater. Now, in the process, if your HU design, the structure, the structure of the air handling unit is not proper, I'll just take only one example because there are lots of things to talk about it. Just one example is how you need to be really careful with selecting your products that actually deliver the final end results for the utilities for the end users. The wall thickness, there are two walls I just mentioned, the inner wall and the outer wall, and there is an insulation in between them. Now, this wall is not supposed to transmit the coolness inside the HU to the heat outside in the plant room. You understood? So this transmittance value has to be as low as possible. If the transmittance value of the HU's walls are as low as possible, which means you're not losing energy from the HU because you're working the chiller very hard to bring down the temperature and then putting it into the air. Air then cools and gets cooled and delivers into the space like the theater where surgery is happening. Now, if I have to deliver 16, it's really very cold air and high humid it will be. So obviously what happens if your thermal transmittance value, which is the U value, is higher, then this particular 16 degrees will get lost to the outside ambient temperature very fast. And in the process, the cooling will be affected inside your theater. Not only the cooling gets affected, your chiller will have to work overloaded to maintain the temperature because it's saying that I'm not able to get the temperature in the room. The valves will be fully open at the same time, the chiller gets onto full load. Now, when you select an air handling unit, make sure that the classification on the left side, T2, is the classification as per the Eurovent standards. It says the U value should be between 0.5 and 1 watt per meter square Kelvin. This particular value has to be there when you select your HUs. If it is not there, and unfortunately, if you've forgotten to check that, and if your HU vendor has given you an HU which has got a value of 3, the transmittant value is just double of it. Now, when it is double of it, look at the right side table, the third line, it will have a heat loss of 700 watts as against 500 watts for one U value 1 as against 250 watts for a 0.5 U value. So here, if the energy is going to get lost every second at 250 watts compared to 700 watts for a poor HU, you can imagine the HU is going to run 24/7 for 15-20 years. You are going to have enormous amount of energy loss, enormous amount of cooling issues in the theater. Every time you will have a problem of condensation on the HUs. Whenever there is condensation, obviously there is going to be fungal growth, infection control, contamination issue. You're actually going to add on to your problems. So I picked up only one issue why you need to be careful with your selections, why you need to be careful with your control of the operations and maintenance of your air handling units. Now, coming back to the NABH standards, infection prevention standards, IPC4, it also says very clearly that you need to have appropriate engineering controls to prevent infection. It could be either spacing the patient beds, we had, Jamila talking about protective environment and negative pressure isolation. These are all the space settings that are mandatory for each requirement to bring down your infection that's likely to happen. So your design of the patient care areas should be very appropriate to the design requirements to bring down the infections. Second part is air quality checking, monitoring the, as mentioned before, real-time monitoring of all the equipment's performances, real-time monitoring of the air quality, temperature, humidity, checking the HEPA filters once every 6 months. There are various things that comes in as all of them connected finally with the infection control prevention measures that you will be doing within the hospital. Now look at the design. Now here, now if you look at it, this is a particular design of an operation theater complex. Now here, this is operation theater 1, 2, 3, 4, and 5. You have the sterile corridor in front of them. You have the pre-op areas. So there is a semi-sterile corridor where the patient gets wheeled in, comes to the pre-op area. After the initial PAC checks, the patient is wheeled into one of the theaters. Now, once the surgery is done, the patient is moved out and comes back into the sterile corridor, either through the goes to the post-op, depending on what kind of surgery, how the post-op areas are going to be designed in and around the OT complex. Now, behind every operation theater, you have a dirty utility or a unsterile corridor for the movement of contaminated materials, and that goes out to the separate lift, and that moves out into the biomedical waste area. So you can make sure that, this is the HU room. So you have a dedicated HU for the corridors. This is the space for HUs for the dedicated theaters. Each theater having its own space for an HU. Like Jamila mentioned, you can have the HU room just above the theater, or you can have HUs placed beside the theaters itself, so that you are very close to the air handling units. Then you have the changing rooms, the toilets, wash areas. All these basically makes you to have a proper design layout. Basically, why I'm trying to tell you is contamination control is not only because of environment, it's because of people movement, material movement, and unwanted door openings of the theaters, unwanted door openings from between the sterile corridor and semi-sterile, between the semi-sterile and the non-air conditioned corridor. So obviously all these, suppose suppose I'll just give an example. This is your semi-sterile corridor and this is your sterile corridor. If, for example, the air conditioning unit in the semi-sterile corridor is not going to function, what happens is the positivity of this area gets lost, and then the air leakage from the theater gets faster into the semi-sterile corridor. Your temperature control and positive pressure control inside each theater is going to be affected to a larger extent. Now, this will affect your performance levels of the contamination and infection prevention within each OT. Now, that's why these air handling units, wherever they are located, should be easily maintainable. So your designing of the area should be such that the issues are maintainable and they are actually in a system that it always runs correctly without any issue. This is one kind of a design. NA-based guidelines, I think already Jamila went through that, so I'm not going to go through them. The basic NA-based guidelines for the OTs. You need to make sure that all these parameters are generally checked before you bring in the patient for the surgery. Now, let me come to the JCI standards, which is the 8th edition. It talks about risk assessment and monitoring. See, risk assessment is another option of identifying the problems that are waiting to happen. Right? You don't want the semi-sterile corridor HU to break down and create a havoc with the contamination control. What can be done is basically is how good you're having a risk assessment for your entire utility management system. You should also make sure that every department has its own KPIs for identifying the best performance requirements for all those equipments in those areas to make sure that you are giving your performance 100% to the requirements as per the clinical aspects are concerned. At the same time, you're reducing the risk of breakdown and reducing the risk of any problems because of equipments not performing very well, and finally leading to safety issues, life safety issues, or infection control issues. Then coming to chapter 8 of 8th edition, it talks about having a proper program for the utility management. Every system has to have a program, SOP or a program or a manual, which tells how the whole process works from morning to evening, what all the systems are available in the process that enables the full delivery of services for the different aspects of the building. So this particular utility management program has to be revisited every year, and for any additions or changes within the hospital premises, like if you're adding one more OT complex, your program has to be updated. Suppose you come across a problem and you're changing your process flow, you need to again update your program. This basically ensures that you're following the system of maintaining all critical equipments within the complex or clinical areas in such a way that they are always tested and you're always above the problem. You're not waiting for a problem to actually occur. Next is FMS 8.04 specifically talks about mechanical and engineering controls. See, as again, I come back to Jamila's point of talking about real-time monitoring. If you do not have apparatus, sensing apparatus, automatic control and monitoring system, BMS, building management systems, IAQs, indoor air quality, controls, all these are basically going to give you the real-time data, what's actually happening within the operation theaters and ICUs and critical areas like your biomedical equipment rooms like MRI, CT, LINAC, etc. Unless you get the data, you will really not know what is going to happen. So the standards also tell us that you are supposed to have good and viewing systems to actually make sure that you are able to get the data, which actually tells you what conditions are prevailing in the different areas of the hospital. Coming to AACI, which is American Accreditation Commission International, as part of 10.1.3.0, risk assessment again becomes important for the integrity of the physical environment. Physical environment basically is your facility and facility management. If you do not have a risk associated management or assessment system, which is finally going to affect your patient care, then you're going to be in real trouble. So risk assessment, like for example, MRI. You need to have a separate risk assessment program for the MRI unit as such, for the MRI equipments which feeds the utilities into the system. Then the fire safety issues, water issues, fungus issues. There are various kinds of parameters that are actually likely to come in and pose a risk and a hazard for your system. Coming to 22 standard, which is part of infection prevention and control, it very clearly talks about how we should have good ventilation and water quality control in all critical areas. Like even when I talk about water management, we talk about quality testing of water for the physical properties, chemical properties, and microbiological properties. We always tend to forget the dental chair water. We also forget to test the water for the ports for the dialysis units, dialysis ports inside the ICUs. ICUs, generally the dialysis ports are hardly used because generally there's a dialysis port in the dialysis center. So various aspects have to be looked at very clearly to bring down their infection prevention and patient safety issues. Another point which is talked about in standard 22 is maintaining safe air handling systems in areas of special ventilation, including the OTs, ICUs, and all the airborne isolation rooms. Maintenance of air handling systems. So that is going to be critical for you. We talked about in length in the NABH standards. So all the standards specifically talk about proper maintenance. And coming to the standard 28, it says that the organization maintains the utility systems and its processes, which makes it very safe and a reliable system so that you are having the systems working in order to meet the end user's requirements. Secondly, if you have a MOU with a chiller vendor or an HU vendor or a cooling tower vendor or any kind of equipment vendor, there should be a tracking process where the MOU is being tracked. What is MOU? Memorandum of Understanding, which talks about your comprehensive maintenance contract with the vendor. Now, if you do not have a proper tracking process, then you would never know when the preventive maintenance was done, when is the next preventive maintenance to be done in future. Second is, when is the your AMC going to be what is the expiry date of the MOU? So basically, the tracking process of all these documents are also being documented and verified during the accreditation process. So it's mandatory that you have a tracker for not only the assets, but also for all the tracking of all your comprehensive preventive maintenance contracts. This is a AHU maintenance checklist, which talks about the period, planned preventive maintenance. Standards talk about 30 days for all the critical areas and 40 to 45 days for the non-critical or semi-critical areas. So you need to have a proper schedule, which tells you when is the preventive maintenance last done, when is it next due. So you have to have a proper planned preventive maintenance schedule for the whole annual year and a tracking system where you have a checklist for that. And this is your checklist. Each time the vendor goes, not the vendor, either you have a contract to the vendor or you have your own AC technician. He goes with a checklist. The first item is the asset number, asset category, the location, equipment name, AHU reference, so and so. He checks through all these points and then completes the document verification. If he has got any findings, he will take it up with his superior supervisors or engineers to take up to the level of correcting those problems that he has actually envisaged during the or he has actually seen during his maintenance of the particular age. One thing is talking about the parameters that are mandatory that needs to be verified is the temperature, the relative humidity, especially in the theaters, the air velocity. We talked about 25 to 55 feet per minute at the surgical table level. So we need to make sure that that levels of airflow is available, airflow pattern, as an laminar is available, the filter integrity tests. The filters are really in good condition. Is there any problem with the filters? We have to also check the particle count and also set it up for recovery before you hand it over to the team for the surgeries. The commissioning is very important as far as the process flow is concerned. Is basically that it's not like you finish the electrical work and put on a switch and the light is the bulb is burning. Now, when it comes to air conditioning systems, it never starts and stops with that. You need to have a proper testing and balancing method for the commissioning process to complete before you actually hand over to the end user. You need to actually have the air balancing to be done. The air balancing will tell you, as per the design, what is the supply air, what is the return air, what is the fresh air, what are the air changes, like Jamila mentioned, as per the NABH standards, 4 air changes for the fresh air, 20 air changes for the overall air change. These values are available when you actually commission and test and balance the system. So when during the testing and balancing, you will actually identify, calculate, and find out and see that the values that you obtain are exactly in line with the design parameters that was given in the drawings and implemented during the construction phase. So that actually confirms to the design parameters are meeting the actual values that you take during testing and balancing and commissioning are actually meeting the design standards that was intended before the project started. So that actually helps you to have a proper commissioning document before you hand it over to the operation theater team to bring in the first patient. So that's all from my side. Short time to talk about so many things, but I did manage to speak definitely about the 3 major accreditation bodies that are generally and now in the present in the market and in terms of accreditation standards, national as well as international, how they are connected with facility management, how the facility management finally boils down to a proper and safe care for our patients, including the critical care of our system. Thank you very much.
Yes, sir. Thank you so much. And there is a question from Miss Aditi. She's asked which disinfectant is used for cleaning ICU.
Can we go to the next question, which is pertaining to Mr. Vinod, sir?
Yes, madam.
I did manage to answer the few questions when Jamila was on it. Yeah.
Yes, sir.
Any role of air purifier in isolation room in addition to HVAC?
I did mention that, we normally don't provide air purifiers and all. We generally, the air conditioning system should be able to handle the air filtration part of it. Having too many equipments and disinfecting them becomes a difficult aspect within a isolation room, especially if it's going to be negative pressure. So the air handling system should have proper filtration system. I don't think an additional air purifier is recommended anyway.
Yeah, thank you, sir. Thank you. So,
Sir, I have a question, very common doubt which keeps coming on and off. Can we exchange pressure rooms between negative and positive pressure? Because sometimes the consultant feels that if the load of negative pressure patients are very less, can we replace it with positive pressure? Is there an option to switch between negative and positive pressure? Or if a room is constructed for negative pressure, it has to continue as negative pressure?
No, there is no hard and fast rule of how to really manage how many numbers of isolation rooms that you should have, whether it is positive, negative pressure, whatever it is. But when it comes to negative pressure isolation rooms, they definitely carry very highly infectious patients. So converting them quickly into a positive pressure room and putting a patient there is not going to be the right choice in terms of patient care and patient safety. But if your infection control or the housekeeping and infection control is going to be perfect in all aspects, then we can think about having the air conditioning system in a different manner, run in a different manner. That is, an negative pressure system should actually run the reverse so that you have recirculating happening, fresh air coming in and becomes a positive pressure. So the negative pressure aspect can be done. I've seen many people doing it, but it's actually not the right practice or not recommended as such to have both in the same place. Jamila, you
Because
can
the
add on if you can add on.
Yeah, my basic question is the HVAC system or the ducts, we don't clean it often. It's as per the schedule. If we reverse altogether the airflow and pattern, I mean, whatever got filtered through the negative pressure air or through the filters, is there a chance of converting into a positive pressure coming back into the room?
See what happens when it comes to a positive pressure room, obviously the exhaust system is not going to work there. That is one thing. Secondly, since the positive pressure is there and the air can come back in the reverse, obviously that the cross contamination can happen. And cleaning a duct and all is not going to be very easy. I don't think anybody has, I've not seen anyone doing it except for the kitchen ducts, which previously people do it because of the high amount of grease in the system and the possibility of a fire outbreak is always a danger. So we have robotic cleaning for kitchen ducts. But when it comes to theaters, you don't get time for a shutdown, first of all. You don't get time for even a preventive maintenance to happen. So considering that aspect, I think it's better not to have a negative pressure room immediately converted into a positive pressure room. Jamila, you can add some few words.
Yeah. Actually, see, negative pressure system, it is totally, we will be having a exhaust which will be connected to the atmosphere, like that we will be having. So immediately converting to a positive environment, that is not actually advisable.
So this question is actually raised by the transplant team members, where, for example, the heart-lung transplant, a patient who has TB needs a negative pressure room. And if this patient undergoes a transplant after the active phase of TB is completed, and then they undergo a lung transplant, they have to be kept in a positive pressure room. So they don't want to build two different rooms. They want to switch between negative and positive pressure. So that's where their question stands. So I need the advice from the
Understood. But actually, when he is before the surgery, he is totally a different person. So it will be like his air has to be completely. We need to exhaust it out.
Yes.
But when after undergoing a surgery, he is becoming a new person, and it will be like he'll be prone to all infections so easily. So it will be like definitely you need to have a positive environment. That will be that it should not be the same room. Otherwise, see, after undergoing such a surgery and all those things, we will not be able to for a room sake, we will not be able to compensate his safety. So definitely it's not advisable.
Thank you so much. That was really helpful. I think there is a question addressed to both the experts. Which return air system is more suitable? A durable return air system or a sealing return air system?
Ducted return is always safer. Secondly, you're not going to mix up other areas into that. But we need to be careful with the humidity buildup inside the false ceiling also. So if there is no ventilation, that could actually bring in humidity levels in the non-AC areas. When you have return air coming, that area gets indirectly cooled. So that needs to be cautiously handled if you're going to be having your hospitals in the coastal areas and humidity control becomes an issue. Once humidity control becomes an issue, then if you open the ceiling, you can see fungus inside the ceiling areas or on top of the insulation of your ducting, you can see spores of fungus on top of that. So ducted version is always better.
One more same question from the similar person. Does sealing return air system cause any issues such as damage to paint?
Not really.
Not really. No, I don't think so. See, unless what happens is the humidity levels are not maintained, you can have fungus coming in, more condensation coming in, but that generally does not affect the paint as such. It will only bring in microbial bacteria, virus, and fungus. Nothing to do with the paint as such. No.
We don't see, you had already answered this question, sir. How frequently the duct should be cleaned and any role of UBGI in AHU of OT? When Jamila was presenting, can take Miss Jamila, you can answer this.
Yeah,
How frequently the duct should be cleaned?
actually, it should be like, as Mr. Vinod said, that periodic cleaning and maintenance, everything has to be done. 30 days once, all the parameters needs to be checked and all those things. So definitely it should be like maybe three months or at least 3 months once or something like that. It can be done. But how far it is practically possible, that needs to be taken care.
Yeah, that is very correct. But at least as an infection control preventionist, we need to oversee the checklist which is done by maintenance team. Like we are not aware about checklist which is maintained by them. We often keep telling them that maintenance of HVAC system has to be done, maintenance of HVAC system. But from their end, they keep telling us that every quarterly we do wash the pre-filters, we do externally clean it. So as an infection control preventionist, I think we need also to oversee the checklist which is maintained by the maintenance team for us to understand the work, the hard work which is always done by them.
Yeah, even the AH room also should be cleanly maintained.
Yes.
Because
we use that as a storage area actually.
Exactly, sir. One more question, ma'am. I have read UK guidelines regarding this. It states that it's not advisable to convert, but if changing the pressure room, then proper pressure checks has to be done and room should be named as positive or negative. Yes.
It's going to complicate the system, doctor. I think we better not have a room which can be both of that. It's not right, because if you're having a negative pressure room, then you're going to coordinate off from the corridors, right? Anti rooms and things like that. But in a positive pressure room, it's not like that. So obviously, control measures, everything will change. Anti rooms, you're changing or doffing areas, all that is going to change for you.
Exactly.
Like positive pressure room also converting into negative pressure is very difficult.
It's very difficult.
We can make a room positive pressure, but making negative pressure is like hugely difficult for us. It's maybe the gauges will show, I don't know how some places it's like, checklist becoming a tick list, gauges working for the sake of showing the figure, but actually that's not the real figure. So these are things that are happening, but obviously I think we should correct them.
Thank you.
Today, assuming that if one of our relatives is inside the theater, can you imagine what kind of hope we will have on these systems?
Exactly. Well said, sir. Thank you. Thank you so much, sir. So, Afrin, should we move on to the next topic, last topic of the day, or do we have some more questions?
The question is all done, ma'am. So we'll move on to the next topic, ma'am. So the next topic is on environmental solutions to mitigate airborne transmission, which will be presented by Dr. Yamuna Devi. She is a consultant in infectious prevention and control, CSSD HOD, and OT coordinator at Apollo Hospitals, Chennai, a gold medalist in anesthesiology and clinical microbiology from Madras Medical College. She is board certified in infection control, CVIC USA, trained in outbreak management by Johns Hopkins University, and a certified simulation trainer. She is presently pursuing an MBA in ISB and had led several award-winning infection control initiatives. Please, ma'am, talk about the topic environmental solution to mitigate airborne transmission.
Thank you so much, Afrin. I think my work is halfway done by all the speakers, wonderfully done. So I may not have to spend a lot of time on the mitigation measures. So my topic is environmental solution to mitigate airborne transmission. So this is a very good saying given by Louis Pasteur that when I meditate over disease, I never think of finding a remedy for it, but instead a means of prevention. So in a hospital sector, when we think about who is at risk, everyone who walk into the hospital, right from the healthcare provider to patient, to the attendant, to the intern, to everyone working in the hospital is at risk. And how hazardous is healthcare worker as compared to other ultra-safe units is the danger for healthcare work, healthcare related work is there is more than one of death or total lives lost per 1,000 events taking place. But when we look into the ultra-safe industry like an airline or a nuclear power industry, it is less than 1 to 100 million. So the problem what we face on a day-to-day way is in airline industry, it is 1 death per 19,23,750 passenger departure, whereas in a healthcare industry, it is 88,000 total nosocomial infection and 1 death per 396 admissions. And around the nosocomial infections, 4,400 airborne diseases happen, and out of which 1 death happens related to 7,930 admissions. So 3 numbers are usually very important when we talk about healthcare performances, where 60% of care on average is in line with evidence or consensus-based guideline. 30% of care, what we do is waste or of low value, and 10% of care is absolutely associated with patient harm. So we have limited progress over this last 30 years and indicating the need for new approaches in order to improve the care quality. The risk factors as far as TB in Indian healthcare provider is related to the body mass index. If someone is malnourished, of course, they do get TB. Frequent contact with patient, if they are employed in medical wards, employed in microbiology laboratory, and the risk as far as occupation-wise, the risk is very high for people who work in lab because it's a very closed area. And if the specimen is not properly processed in a biosafety cabinet, the exhaust is not working well, people are overtly exposed to it. In emergency rooms where we don't know about the patient's condition and people are not strictly following the personal protective equipment policy, then of course they are also at a very high risk. Third, the inpatients, and finally the outpatient facility where the healthcare providers are seriously at high risk. Patient-related characteristic, all patients are not the same. Depending on the patient characteristics, the risk related to infection is also very high. For example, someone who is a coughing patient and failing to cover the cough, aerosol generating procedure, if the viral load of the patient or the bacterial load of the patient is going to be very high, diseases of the upper respiratory tract and tract like larynx or lower respiratory tract, of course, the risk is high. Cavitation present in the chest X-ray and inadequate TB management. Procedure related, if it's an aerosol generating procedures like bronchoscopy, endotracheal intubation, or open abscess irrigations or autopsy, sputum induction, all this puts the healthcare providers at a heavy risk. And of course, the environmental factors and risk for transmission, like an exposure in a small enclosed spaces where the ventilation and the air circulation is very less, when the recirculation of the infectious droplets, which is liberated into the air by the patient sitting in the corridor or sitting inside an area, inadequate cleaning and disinfection process, improper specimen handling, inappropriately maintained HVAC system, cooling towers, or the food exhaust system, which is kept in the laboratory, all these environmental factors puts us at a very high risk. The impact of microbial contamination as far as HVAC system goes, it's predominantly spoken about the mold infection, which Dr. Anup has also mentioned that it's predominantly mold infection, which is spoken about whenever there is a failure in the HVAC system, let it be related to improper maintenance or let it be related to the construction related activity or the cleaning activity or loss or contamination of the insulative materials around the HVAC system. Why we talk more about airborne infection as a reason of causing the reason of transmission of infection is the airborne particles spread to a larger distance as compared to droplet-related infection. The airborne infectious droplet nuclei can spread to a larger distance from 5 feet to more than 160 feet. And variations in respiratory emission by activity as compared to someone talking, only 35 load of bacteria or viruses are liberated, whereas someone who is coughing, there is far more 371-fold increase in the release of these viruses and bacteria. And also, as I mentioned, it depends on the number of copies or the viral load which is present. More the viral load, more is the secondary attack rate. When we talk about R0, it also increases as the R0 number increases. For the measles, the R0 is 18. That means if one person in a room is infected, he can tend to infect 18 odd people within the same room or nearby area with measles infection. So when we talk about infection prevention, the chain of infection plays a very important role where we need to address each and every component in order to prevent the spread of infection for the susceptible host. So the fundamentals of infection prevention depends on 3 factors, and that's the reason why we had chosen environmental control, which is the most important among the hierarchy controls of it, like elimination, substitution. The engineering control is the third most in the important hierarchy controls by which we can prevent the transmission of infection, whereas the PPE comes in the last. If we wear PPE, it's an additional protection, but where we need to concentrate more is on the engineering control. The purpose of engineering environmental control is it controls the source, it dilutes and removes the contaminated air, and controls the airflow also. The areas where we need to look into these controls is already specified and it's already spoken about by the experts, but the additional area which we need to focus on place is also the laboratory. So this was not part of the discussion, but of course, when we talk about high-risk areas, microbiology laboratory or the molecular lab where they process the specimen with patients coming with respiratory illness has to be taken care. So the risk mitigation measures can be with n number of phases or n number of practical control measures. One, the pressure management, already spoken. Room air exchangers for dilution, ventilation. Filtration is the third modality. Maintenance of temperature and humidity control. Appropriate physical barriers. We will see a little bit more about the ultraviolet germicidal irradiation. Phased construction renovation activity. How do we do the surveillance maintenance, which was already spoken about, Mr. Vinod Kumar, feedback and training and monitoring aspect. So this is the summarized picture, what we have been discussing in the last 2 hours for the air pressure, room air exchangers, how much sealing has to be provided, the filtration supply and the recirculation for airborne isolation, positive pressure or the protective environment in a normal critical care area, in an isolation room and an OR. When we talk about airborne isolation room, there shouldn't be any recirculation. When we talk about other rooms, recirculation can happen. So airborne isolation room and the isolation anteroom area air should never be recirculated into any part of the hospital. When we talk about the positive pressure room or the protective air environment, the filtration aspect is somewhere around 99.97% because we need to have a HEPA filter at that point of area. When we talk about general critical care area or room, the filtration level or efficiency is more than or equal to 90%. It's not equivalent to 99.97%. This difference we all have to identify whenever we talk about critical care area. So in critical care area, since it's going to be only around 90%, we cannot completely eliminate anything which is around 0.3 microns, which also includes the fungal spores. So the number of isolation rooms, as we were discussing, how to determine the number of isolation rooms. This is one of the guidelines which I could pick from International Healthcare Facility Guideline and also CDC, where they say you need to do a infection control risk assessment to determine how many isolation rooms, particularly how many negative pressure isolation rooms you would require. You should also look into the trend of disease in the general population and the demographic trends of the population catchment area where your hospital is actually serving, and also look into the specialty services which you are giving to the patient. So negative pressure isolation room requirement, at least 1 negative pressure room per 100 IP beds is the minimum requirement. For positive pressure room requirement, there is no standard which says these are the minimum requirement of positive pressure room. It all determines, or it's all decided within the healthcare system or the management based on the population you serve, like a transplant patient or a BMT patient or a number of operation theaters you need to have. So those many positive pressure areas has to be created. I'm not going in depth of this airborne isolation room because it was already discussed and told about, but the airborne isolation room supply air filters only about 90%. The minimum air exchange should be 6 to a maximum air exchange of 12, and the pressure difference should be in negative 2.5 pascals. You need to have an appropriately sealed room. You cannot have too much of gaps below the door, below the corridor, across the door, or above the door. You need to have a sealed room. So the maximum leakage which you can allow is 0.5 square feet. Remaining all was already discussed. So never have recirculation of air from the airborne isolation room into other areas of hospital. If you are doing, you have to have mandatorily HEPA filter. So this is a structural alignment of airborne isolation room, which was already discussed. The airflow pattern. Isolation room, what is more important is the pressure gauge, which has to be checked on a regular basis or in every shift by the bedside nursing. It has to be charted on a regular basis. The next most important is PPE control before you enter into the negative pressure. Positive or a protective environment. The supply air is always filtered to an extent of 99.97% because it gets filtered through the central or point of use HEPA filters, and the air exchange should be around or equal to or more than 12 air exchanges. This is how the positive pressure isolation room needs to be installed. OT, it's been well discussed by our previous speaker, Ms. Jamila, about two different types of OT, what is needed, how big the HEPA filter has to be located, how the return air and how the exhaust air has to come. One more important aspect of air exchange and the quantity of the microbes or the bioload which has to be removed is, if we talk about in an OT as far as NABH standard goes, and we say the air exchange of an OT is 20, that means the entire cubic volume of air present in the room has to be completely exchanged with another set of fresh air supply, which is around 4 to 5 fresh air supply in the OT. It would take 7 minutes if you need to remove 90% of bacteria or the viruses. 99% would be removed within 14 minutes and 99.9% in a period of 20 to 21 minutes. This is very, very important when we talk about an operation theater or when we talk about shifting of patient and receiving another patient into the same room where I'm going to station. We need to give minimum 21 minutes time if the air exchange is going to be 20. And in an ICU, if the air exchange is going to be only 6, the efficiency is around 69 minutes. So I have to literally wait 69 to 70 minutes in order to maintain that much efficiency of the contaminant to be removed from that area. The third aspect is, can I have HEPA filter in the zone if I do not have additional air filtration, or if I do not have an appropriate HVAC system in the place? Can I have it? The answer is, it's just a supplement to the ventilation. It alone or standalone, as already the experts have told, is not going to help us out. And standalone air purifier is totally different. What I am talking is the standalone HEPA filter. So it says it supplements only the ventilation if it is installed inside the HVAC system, and it removes about 99.97 of particles more than 0.3 micron. It must be used in places where discharging air from the local exhaust booth directly into the surrounding room. Second, when discharging air from the airborne isolation room into the general ventilation system. It can be used to clean room that is exhausted to the outside. So this was already told about the pre-filter level 1 and the pre-filter level 2. So whenever it is a protective environment, we always have 2 bank of filters. One, which is 30% efficiency MERV 8, filters it out. And the second one is the HEPA filter, which filters completely 99.97%. So depending on the type of room, depending on the type of patients you are going to admit, the level of filter bed has to be determined. You can't keep putting HEPA filter everywhere wherever it is not required, because it adds cost for the hospital and the organization. The fourth aspect is the distance between the patient and the infection. So if there is an index patient, the more and more proximity you are to the patient, the chances of acquiring infection is very high. Whereas the more and more distance you are away from the patient, chances of getting an infection is very less. This is what we describe about the physical barriers, or the distance between each bed within the hospital, or can we create a normal physical barrier in order to increase the distance between each patient sitting in the hospital. The fifth aspect of mitigating the airborne or the mitigating or reducing the airborne particles are, can we have a UVGI, that is the ultraviolet germicidal irradiation, which is very well described in WHO guidelines as an additional or a supplemental to the ventilation. It kills about 64% of MTB in 24 seconds and 99% in 2 minutes. And the efficiency is equivalent to 10 to 20 air exchange. But it has to be used as a supplement to ventilation and not as a substitute for negative pressure. It is not a substitute for HEPA filtration when air is recirculated from AI room to other areas. Use in high-risk areas where adequate ventilation is not achievable, particularly in outpatient department where you can't have a dedicated AHU or a HVAC system supplying in that area. But what we need to be very careful when we install UVGI in those areas is overexposure can cause damage to skin and eyes. So the upper room UVGI should not be used in rooms with ceiling heights less than 8 feet. And all the upper surfaces, wherever you are going to install, should have a reflectance of less than 5%. And 30 watts of UV lamp power are required for a minimum area of room of 200 square feet. So these recommendations has to be followed if you are planning to install a upper room GI, upper room germicidal irradiation. This is an example how the UVGI rays can be installed in patient care rooms where you do not have an appropriate ventilation, like an outpatient department, or your outpatient department is situated somewhere in the basement of the hospital and you tend to get a lot of infectious patients. This can be a savior for you as a supplement to the existing system of air handling unit. So this also tells that the amount of germicidal strength away from the distance is that this is the minimum most germicidal agent which can be generated at a distance of 15 feet, around 10 microwatts per centimeter square. So at this level, between 3 feet, it is around 200, 5 feet, it is around 100, and at 7 feet, it is around 50. So this is the area where you have to determine the strength of UV radiation you would require wherever the patient is breathing and accordingly fix it. The last thing is about, can we have a UVC in duct air and surface disinfection? So if you are thinking about putting a UV germicidal in duct or for surface disinfection, it can be installed either perpendicular to the airflow or parallel to the airflow. But there are two different aspects to it. Are we looking into keeping a UVC for air disinfection, or are we going to put UVC for a surface disinfection of the panels or the AHU? So if I am going to put a UVC for air disinfection, all the air which goes through the duct, then the minimum target UVC dose should be 1,500 microwatts per centimeter square or joules per centimeter square. It is designed for 500 flow per minute or slow moving airstream. Minimum irradiation zone, the size of it should be around 2 feet, and UV exposure time should be around 0.25 seconds. And it should be coupled with the mechanical filtration as it does not compromise the system performance. This is an additional layering of technology in order to increase the efficiency of air cleaning. But when we are putting UVC in duct for surface disinfection of the AHU in order to reduce the mold growth within the AHU or reducing the dust particles settling in the AHU, it has to be focused and installed near the cooling coils, drain pan, and other wetted surfaces. And the irradiation which has to be needed for surface disinfection can be lower as compared to the in-duct air disinfection. The goals are even distribution of this UV energy across the coil face, and generally it is 12 to 36 inches from the coil face. This is one more guideline which is given by the Ministry of Health and Family Welfare, that if you have patients for whom you need to induce cough in order to collect sample, particularly outpatient department, where you see a lot of TB patients, this is a specification at which the sputum booth has to be constructed with a minimum air exchange of 20 to 24. And these are the special conditions or the ICRA matrix, which has to be done whenever you are going ahead with a construction and renovation activity in order to reduce the airborne disseminated in the place wherever you are keeping patients. So it depends upon two different aspects: the type of patients you are admitting. Second, the type of construction you are trying to do. Is it a type A, B, C, and D? Depending on that, the prevention and control measures has to be taken care of. As already spoken by our first speaker, Dr. Anup, regarding the sink installation, where and how and the shape and size of the sink which has to be done. This is a very good document given by WHO in order to prevent and control the spread of carbapenem resistant organism, where they clearly say that sinks should be placed near the ICU entrance. If this is not feasible, you can keep waterless hand dispenser, but never keep a sink within the patient care room or within the patient room. An adequate number of easily accessible elbow or foot operated sinks should be available. And this is a complete focus on clinical hand wash basin, where they talk size of the wash basin, the hand hygiene product, installation, tap and faucet, plug should never be kept in the sink, and the shape of the tap should never be in a swan neck shape, because that would lead to increase in accumulation of the water and thereby bioburden and biofilm production. Always have an appropriate microbiology data. Do not have a knee-jerk reaction. Do not react to all the microbiology report for all the samples you do. The first thing is, do not send unnecessary samples because everybody asked for a sample. Have a written protocol for the sample collection. Always set a benchmark or target for interpretation depending on different area. If it's for OT, what am I going to do? If it's for ICU, what am I going to do? If it's for transplant unit, what could be the interpretation? And compare the necessary with outdoor control, which sometimes needed whenever you're doing a construction renovation activity, where I want to see the bioburden of fungus within the construction area as compared to the outside area, because I do not want the same air to come outside the construction zone. So that level of comparison would help me to make sure that the area is completely barricaded and prevents the spread of aerosol. Qualitative and quantitative analysis can also be done. So it is your microbiology interpretation data which has to be clearly determined in the organization, so that it doesn't confuse the clinical side of people and also the non-clinical side of people, that what they have to do in order to prevent infection. Future direction is already spoken about our speakers, like smart building, where it can adjust the ventilation based mechanism, AI driven system to predict the maintenance and efficiency, that it's going to be summertime in the month of May, June. What should be the ventilation level? How should I predict the humidity and the temperature control within the OT? So these are some of the futuristic direction where engineering controls and team are working forward. So this is my last slide. Let us pledge not to repeat the history. This is the famous building where the legions met in the year 1990 or 1970, where there was a big outbreak of Legionnaires' disease from the cooling towers. How did the air from the cooling tower entered is all because of the aerosolization of the water from the cooling tower, which entered into the place through which the air was supplied into the room where all the veterans were sitting, and thereby they ended up having a Legionnaire's disease. And they had a mortality of as high as 30 to 35%. So let us pledge to maintain the HVAC system in the hospital as already taught to you by the expert panel members, by the expert people who were very good enough to explain in a very appropriate, collaborative manner, and also in an explanatory manner, in simple words, how we need to maintain the system in order to prevent the spread of aerosols within the hospital. Thank you.
Thank you very much, madam. So here is a question. Dr. Anaga has asked, role of microbiologist in air quality control.
So role of microbiologist in air quality control is, of course, going in hand with the maintenance team. So they cannot function as a separate unit. They have to work together with the engineering team and understand the maintenance part of it, the duration at which the maintenance has to be done. And depending on that, they should be the liaising people with the OT or with ICU. Many times we see that the operation theater is not given for maintenance at all. There will be a due for HEPA filter change and the doctors will be operating continuously. So that is the main role of the infection control specialist or the microbiologist to pitch in and tell the team that this is a high time to change the HEPA filter, or it's a high time that we go for a maintenance of the operation theater, because the maintenance people, they many times feel it's a very delicate situation for them to go and talk with the clinician. So that is the main role. I believe that the liaising people can do in order to bring all the clinical and non-clinical side together. And also air quality control, as we have recently, the NABH guideline 6th edition has mentioned there is no role for repeatedly doing the cultures. What we need to look into is the temperature, humidity control, the pressure control inside the OT. If that is taken care very well, we do not have to do cultures of the OT repeatedly.
Thank you, ma'am. Thank you, ma'am. So there's another Dr. Hafan has asked for the PPT. It was such a complex topic has been presented in a very simple manner for the understanding purpose. So if possible, we might need to share the PPT also, ma'am. Anyway, thank you so much, ma'am. So it was very useful.
So yeah, as Mayank has mentioned that there are no more questions. I would really like to thank Mr. Vinod sir, Ms. Jamila madam for coming together, spending their precious time for 2 hours, sitting for a session on a webinar for 2 hours, that too in the late evening from 7 to 9 is not at all a joke. Thank you for accepting our invite and making yourself available and creating PPT, which is very useful, simple for doctors like us to understand. Because whenever we talk about HVAC system, we say it's a role of maintenance. You please take care. You tell us what we need to see. But it was really wonderful to explain in a very pictorial way what is needed and what as a doctor we need to know about it. So that was really wonderful. Thank you so much. Thank you, Dr. Anup sir, for bringing us the challenges which as a doctor on a day-to-day practice we do face. Whenever there is an outbreak, it keeps itching our head that from where did it come? Is it from the environment? Is it from water? Is it from the surface? From where should I begin with? So that's a wonderful challenge. You brought it up, sir, as an opening session, as an opening batsman for the session. And thank you all. I would like to hear out the feedback from our speakers.
Yamuna, first yours. Sorry, Jamila, yours.
Please.
Yeah, thank you so much, ma'am, actually, for this opportunity. It's our pleasure to be in this conference. Actually, I was just slightly, what to say, in front of doctors and nurses and in the medical forum, how it is going to be like that. I was just thinking in my mind, because it is a total different kind of audience. But it went very well. Thank you so much. Thank you so much for this opportunity as well. It is our pleasure to be part of this AMR Trust webinar. Thanks.
Thank you so much, ma'am.
Thanks, Jamila. And once again, thanks to Dr. Yamuna and Afrin, and as well as the AMR Declaration Trust to give us this opportunity to speak on this forum. And it's always a pleasure to give our knowledge to people. And the way, and as Jamila mentioned, the audience is quite wide. We'll have engineers, we'll have doctors, microbiologists, anesthetists, surgeons, every kind of people would have been in the audience. So it's actually good and a pleasure to give our thoughts and knowledge to such a big audience. So thank you for giving us this opportunity. And do call us for more programs. We are ready to do it.
Thank you, sir. I would like to thank Kafoor sir for creating this AMR Declaration Trust so that people all across the world are benefited by knowing how to prevent antimicrobial resistance across the healthcare setup. And thank you, Afreen, for coordinating the session and all the speakers. And also thank you, Mayank, for coordinating with the people who have connected through a different line and bringing up all the questions to us. Thank you so much.
Thank you.
Have a great evening and good night.
Thank you, ma'am.
Bye.
Thank you. Yeah, good night. Thank you, Afrin.
Thank you, Afrin.
Thank you, sir. Thank you, sir.